Very good evening, all. Welcome to problem solving session number 6 for the course Mechanics of Material. So, this week, again, this week's session, we'll see some problems from week 6 topics, especially the Borley Valley problem solution to axial members. So let's start. Before we start, I want to just go through these thing again, once again. So we started actually the course with these four concepts of mechanics, the basic concepts of mechanics. So we saw force and displacement cannot be related directly. They need to be related indirectly through some other concept. So we introduce something called stress, and we introduce something called strain, and we also saw this relation between force and stress we called as equilibrium equation, and this relation between the stress and strain we call as constitutive relations, and the relation between the strain with displacement we call as compatibility conditions or compatibility equations, and the relation from displacement to strain we called as strain displacement relation, right? Relation. And through this, we actually connect the force and the displacement. Okay. So this is how we actually started, and in week one, week two, week three, week four, week five, we have seen various concepts like force, displacement, and then stresses and strains. Fine. So this week, from this week onwards, we'll see one by one how to apply these concepts in case of real life problems. So this week we'll focus on axial members. Then we will be having flexural members, then members subjected to torsion, then cylinders, the columns, the lot of things which is upcoming. So this week we'll focus on how to solve the problems related to axial members. Fine. So suppose if we have a bar subjected to thing like this, say a force, some P is there. Now using these concepts that we have studied, how to relate the force and the displacement. So displacement will be this delta. This bar is now elongated to delta. So this displacement we call delta. Now how to relate? Say suppose if we have this stress tensor sigma is equal to P by A 0 0 0 0 0 0 0 0, and the corresponding strain tensor will be say that is delta and this is L. So this will be delta by L 0 0 0, and delta in thickness in the y direction by x 0 0 0, and delta in z direction divided by say b and h are the dimension of the other side. Now if I take sigma xx, I am considering majorly only the sigma xx component. This is equal to nothing but p by a, right, where a is the area of the cross section. Fine. This is coming from equilibrium equations. equilibrium equations. Suppose if we use constitutive relation, we say sigma is equal to one-dimensional constitutive relation. If we substitute sigma equal to epsilon E, so this will give rise to P by A is equal to epsilon E. Now, if we use the strain displacement relation, epsilon equal to delta by L. Now, when we substitute it back, see, our aim is to relate this P with delta. We cannot do it directly. That's why we are using these concepts indirectly. So, this will be equal to P by A equal to delta E by L. Now, this delta will be equal to PL by AE. Okay, this is the formula for displacement given for a given force. Okay, this is the relation which connects the P with delta. Fine. So we will use this particular formula in all the problems that we are going to solve one by one. So we will see some variety of example problems of shaft subjected to axial loads. So dive into problem number one for the day. Okay, suppose if I have a shaft like this is A, this is B, this is C. There are two diameters. Okay, this is circular diameter variation is there, so it's stepped shaft. And if this is given as, let me mark the dimensions. This is uh, 2L, and say this is L, and say there is a load acting at this point B. This is P. So all the dimension is given, and this is diameter 1, phi 1. This is phi 2. Okay, this is steel. So it's given that the Young's modulus is 200 gigapascal, and diameter 1 is given by 20 mm, diameter 2 is given by 10 mm, and length, this L value is given by 10 centimeter, and P value is given by 100 kilonewton. Okay, now what we have to find is that we have to find displacement at P, displacement at B, delta B equal to what? Similarly, displacement at C, delta C equal to what? And stresses in AB portion, that is sigma AB equal to what? And stresses in BC portion, sigma BC equal to what? Okay, these four questions we need to find, right? So that's it. Now, how to solve? So there's no need to solve. Actually, we go step by step. We write equilibrium equation, then we write constant relation, then strain displacement, then compatibility condition to solve the problem. But since we have already this deformation formula, we are going to directly use into the problem. But anyhow, the first step is going to be drawing the free body. So let's begin the solution. So the first step here is about drawing the free body diagram. Let me draw. So what is free body? Free body diagram is nothing but the same diagram of this body by removing the supports and showing the forces, internal forces inside. So let me draw it separately. AB and BC. So here there is a force acting, that is P. Fine. Now I removed the support at the point A, so I need to show some reaction force at A. So it should be according to Newton's third law. Every action there is an equal and opposite reaction. So for P action there will be a negative P in this direction. So, right, and BC there is no force, so it's not subjected to any force. It's just staying as it is. Fine. So that's it. This is the free body diagram. Now let's solve one by one. So what is the deformation in the bar AB? So AB is undergoing a long elongation. So maybe I can write delta AB is the elongation in AB. It is nothing but uh, P times the length is 2L. So 2L by area is, okay, area we need to find by the way. So A1 will be pi by 4. D square is 20 square. A2 is pi by 4 and 10 square. Uh, Maybe if I consider this as my A, if this is my A, then that would be 4A, right? So where my A is pi by 4 into 10 square. Okay, for calculation purpose, I am just writing it. So 2L, area here is 4A into Young's modulus E. Let's substitute it at the end so that it is not more tedious in calculations. So P into 2L into a fine. So this will become PL by 2A. Fine. So this is delta B, AB. Now I want delta B, okay, displacement at delta B. What is displacement at delta B? It is nothing but, this is nothing but delta B minus delta A. Delta A is what here? 0, because it's fixed support. So this vanishes to 0. This is nothing but delta B for me. Okay. I can substitute now the values to get the final answer. So delta B is equal to, what is P given? P is 100 kilonewton. So 100. And here for units, we are going to do everything in Newton per mm. Okay. So force will be in Newton, and the length dimension will be in mm, so that it is consistent. Okay. Why I am taking Newton per mm square? Because megapascal in stresses, we mostly deals with megapascals. Fine. And the E values also we convert it to megapascals, which is Newton per meter square. 10 power 6 Newton per meter square or Newton per mm square. Okay, both are same. So this is equal to 100 into 10 power 3. Length is 10 centimeter. 10 into 10 is 100 mm by area 2 into pi by 4 d square. D square, what is my diameter? Is 10, right? So 10 square into E. E value is 200 gigapascals. So 200 into 10 power 3 megapascals. So this is equal to this 100 and 100 will get cancelled. This 10 power 3, 10 power 3 cancel. 1, 2, this 2, 2, 4. So it is 1 by pi is left. So 1 by pi is my uh, deformation, displacement of B. By pi is what? Let's use a calculator. 1 by pi is nothing but 0.318 mm. Okay, this is delta B. Okay, first part, first subdivision is done. Now, second subdivision, delta C. How to calculate delta C? Delta C equal to what? So delta C is nothing but we have to check for the compatibility here. Yeah, delta T is nothing but delta B. Actually, delta BC, we could have written delta C minus delta B, right? But delta BC here is 0. So delta C must be equal to delta B, because there is no force, and the bar, the portion BC is going to be remain as it is without any deformation. Yeah, of course, it's going to have a rigid body translation because of a displacement at B, but there is no internal deformation which is going to be seen. So delta C is nothing but 0.318 mm. Okay, that's it. So this finishes part B, and part C is stresses. Stresses. So part C is stress in AB. Stresses in AB, sigma AB equal to, this will be what? Force in AB divided by area of AB. Area of AB, right? Area of what? That is 4A, right? So what is force in AB? This is equal to 100 into 10 power 3 divided by 4 times pi by 4 into 10 square, right? So this is, so it is 1000 by pi megapascal. Okay, 1000 by pi, which is, I'm getting 318.31 megapascal or Newton per mm square. Okay, this is sigma AB. Right now, finally, stresses in stress in BC. Sigma BC equal to P BC by area. Okay, area of that bar is A. This is A. This is 4A. Now, is there any force in BC? No. So, stress in BC will be 0 megapascal. Okay, that's it. Simple. Fine. So this is only step shaft. Now let's move on to the next problem. Second problem for the day. Problem number 2. Say suppose if we have the same stepped shaft, and in addition to that, we also have a load at the end. So already here there is a load as it is, no change, but plus we have another load here at Q. Okay, this Q, maybe we can take it as 50 kilonewton. Okay, other things are same. And the other dimensions, the dimension of the shaft, the diameter, area, then length, elastic moduli, everything is same. Only thing, we are having extra load at C. So here when we take A, B, C, so what is the first step? First step is drawing the free body diagram. Just a minute. Yeah. So first step is drawing the free body diagram. So it will be, like this. P here, and these are external forces. So I am writing directly. Okay. So we'll come from here. Maybe since Q is acting, so there should be some Q here to maintain the equilibrium, right? And if Q is here, and there should be Q here as well. Okay. And here it will be P plus Q, right? Because both are acting in that direction. So to maintain equilibrium, we need a force P plus Q acting in this side, right? So this is ABC, ABC, fine. So let's start. So same question, we need to find these four quantities. So displacement at B, to find displacement at B, so we already know delta B is equal to PL by AE. Okay, so total force is P plus Q into length. Wait a minute, here did we take the correct length? Yeah, 2L, right? It's not L, it's 2L. 2L by A is 4A and E. So 100 plus 50 will give us 150 kilonewton. I am writing 10 power 3 into length here is 10 centimeter if I remember correct. So length here is 10 centimeter. So it will be 20 centimeter, 20 into, I am converting into mm. So 1 centimeter is 10 mm divided by 4 times area is pi by 4 into d square. D is 10 mm. So 10 square into Young's modulus given is 200 gigapascal. So 200 into 10 power 3. Right? So that's it. Let's cancel it off to find the final value. So 4 cancel. 10 power 3, 10 power 3 cancel. 200 cancel. So what is left? 150 by 100. 150 by 100. So this is 3 by 2 pi. Okay. So when we find the final value, 3 divided by 2 into pi, which is I'm getting 0.4775 mm. Okay, this is delta B for us. Okay, this finishes the first part of the problem. Second part, they are asking what is the deflection displacement at C. So subdivision B, we have to find what is delta C. Now, how to find delta C? Uh, Directly we can write. How about the elongation in the portion BC? Delta BC is subjected to a load Q, so it will be QL by AE. So this is delta BC, which is nothing but delta C minus delta B is equal to QL by AE. Now delta C is equal to delta B plus QL by AE, right? So if you want to find displacement at C, we have to add displacement at B also, because if B shifts by 1 mm, C is also going to shift by the same 1 mm, right? Apart from the deformation of BC, that's what this equation is telling us. So delta B expression we already have. So P plus Q into 2L. Okay, this 2 will get cancelled. 2AE plus QL by AE. So yeah, I would have directly written, but just I am writing it in order to have some general expression. So P multiply by 2 multiply by 2 by 2AE. So 2QL plus QL will be P plus 3Q times L by 3A. So let's substitute everything back. So P is 100 kilonewton, Q is 50 kilonewton. So 100 plus 3 times 50, all are in kilonewton. So into 10 power 3. Length is 10 centimeter, 10 into 10 divided by 2 into pi by 4 into d square is 100 into 200 into 10 power 3 megapascal. So this will be 100 plus 150 is 250. 250. This 10 power 3, 10 power 3 get cancelled. This 100 get cancelled. 1, 2. So this 2 will go up. So pi into 200, right? So this is actually 250 times 2 is 500. 500 by 2 is 2.5. 2.5 divided by pi is, I'm getting 0.796 mm. Okay, so this is delta C. Last problem, both delta B and delta C were same, but in this problem it is not. It is more than whatever deflection we had. Suppose if P is, sorry, Q is in the other direction, might be we would have got a different, lesser value. Okay, for this problem it is uh, adding. Fine. Now, how about finding stresses in AB and BC? Subdivision number C, stresses in AB, which is sigma AB. So sigma AB is equal to force in AB into length of AB divided by area of AB divided into E of AB. So force in AB is P plus Q. Uh, sorry, sigma is nothing but stress, right? So stress by area. P plus force divided by simply area. Area is 4A. So 100, write it here, 100 plus 50 times 10 power 3 divided by 4 times pi by 4 into d square is 100. So 150 times this will contains 1500 divided by pi megapascal. So this is equal to 1500 divided by pi, which is 477.5 megapascal. Okay, that's it. And how about stress in BC? Stress in BC, sigma BC equal to, yeah, Q times Q times L by AE. Okay, Q is 50 into 10 power. Sorry. I am actually writing that deflection formula. So Q divided by A, right? 50 into 10 power 3 divided by pi by 4 into 10 square. So this is 10. So 55 is 20, 200, 2000 by pi. Okay, this is higher. BC is higher. 2000 by pi. Okay, 636.62 megapascal. Why it is higher? Because if you see in the portion BC, it is subjected to two loads, right? So that's why it is. Not because of that. If we take the load Actually, AB is subjected to two loads, so but BC is subjected to a single load. So logically, it should have been lesser, but the area of BC is one fourth of area of AB. So stress is inversely proportional to the area, right? So that's why small area, higher force is there. So we got some higher value compared to BC. Fine. Right. So this completes the second problem. Let's move on to the third problem. Same, moreover, same problem, but if this time we also have a gap. Problem number three, same shaft. Here there is a gap delta. Okay, this is same. Okay, this is 4A and this is A. This is 2L. This is L, and both are E. Fine. Now what we need to find? We need to find if the gap is 1 mm, if delta is equal to 1 mm, uh, what is the displacement of B, that is delta B, equal to what? Where is B here? Same, this is A, this is B, and this is C. Okay. In subdivision number B, we need to find stress induced in AB, that is sigma AB equal to what? And finally, stress induced in BC. Okay. Now let's begin the solution. Now, if we have a problem with kind of gap, so the procedure that we adopt, a easy procedure that we adopt is we assume the gap is not there. Okay, assume there is no gap and solve the problem. Suppose if there is no gap, there is no gap. By the way, there is a load here. I missed it. This P is the load. Okay, there is no other load. Only P is the load. If there is no gap, what happens? If there is no gap, then the free body will look like, free body will be, diagram will be as follows. So here there will be AB, there will be BC. So this is equal to A, B, B, C. For A, mm, there is a P here. Now again, there will be, if there is no gap, what will be there? There will be a stress induced, correct? This stress will be tension or compressive. It will be compressive in nature, right? Because when the bar is trying to expand, this support is not allowing it, so it will compress it. Okay, so I am assuming it as F induced or F compressing. So because of this, there will be a F here. This green one is P. Okay. Now reaction force will be here. If I assume this AB to be in tension, so my reaction will be P minus F. Correct? P minus F is the net tensile force in AB, and BC F is the compressive force. Okay. Now let's find out what is delta B directly so that we can able to relate it. Delta B will be P minus F times P in 2L by 4A times C. So this will be P minus F into this 2 get cancelled, L by 2AE. Fine. This is delta B. How about delta C? Delta C directly it is compression, so minus F L by AE. Fine. Is that right? Is it only minus FL by AE? No. We will be having delta B as well. Correct. This is wrong. So this is delta BC actually, right? This is delta BC. Now I want delta C. So delta BC is delta C minus delta B is equal to this. So this will be delta B plus whatever it is. So minus FL by AE. Okay. So this is equal to P minus F L by 2AE minus FL by AE. So again, 2AE P minus 3F times L by 3AE. So this is delta C. Fine. Now this delta C, we assume there is no gap, but how much delta C is allowed? How much delta C is allowed? Only this delta deflection, this gap of 1 mm is allowed, right? That's what given in the question. So the maximum value of delta C can be 1, right? The minimum value is 0. If it is 0, there is no stress induced, but for the stress to induce, which means for the F to arise, we need at least a deflection value as a displacement value of delta gap, that's 1 mm, right? So I'm going to equate this with delta as given in the question, right? So what will happen, this will give rise to uh, this will give rise to delta C. Okay, we can write the expression for F because we need to find the stresses induced. So we need to find the value of F as well. Before that, the first question was displacement of delta B. Is that over? No, because there also we need the value of F, right? Actually, the question they have asked is delta B, but to solve this, we need to know the value of F, which is the unknown, right? Everything else is known. F is the unknown. This is the unknown. That's why actually we are using this equation. But in this equation, this is known, this is known, this is known, this is known, this is known. Only unknown is F. So we'll keep F alone on one side. Let's see what happens. So P minus 3F times L equal to 2AE delta. This L will come a by L times delta. So this is equal to P minus 2AE delta by L is equal to 3F. So F is equal to P minus 2AE by L times delta. 1/3. Okay. So this is the value of f. Now we can substitute all the values that we have here and solve the problem. But one important point to note down here is our f has to be positive, right? Why I'm saying f has to be positive? If f is positive only, it means compression here because we assume direction like this. If f is negative, it says tension, and it's not possible, right? Practically it's not possible to have a tension in a bar which is actually stretching, so not stretching, pushing down against the wall, right? So f has to be positive. If f has to be positive, then p by 3 has to be greater than 2ae delta by 3l. 3 get cancelled, so p has to be greater than 2ae by l, which means delta has to be lesser than pl by 2ae. Okay. If delta has to be lesser than PL by 2AE. So this actually tells us that if the gap is more, then there won't be any stresses induced, right? The bar is going to freely elongate on its own, right? It won't touches the wall, right? Wall at C. But if the gap is less than this value, whatever this value, this is a minimum gap actually. This can be a question to you. But it's, yeah, let's compute this value by the way. What is this P 100 into 10 power 3 into L is 10 centimeters, so 10 100 by 2 into pi by 4 into d square is 100 into 200 into 10 power 3. So 10 power 3, 10 power 3, 100, 100, 100, 2, 2, 2, 4. So what else is remaining? Delta has to be less than 1 by 1 by pi is there, and everything went. So 10 pi, yeah, right? Okay. So what is 1 by 10 pi? 1 by 10 into pi. This delta has to be less than 0.0318. But R delta is 1 mm, so which means something not right. Let's see. Once again, let's check once again. Is there any error with the value I got? 100 into 10 power 3, 10 mm, 10 centimeter, right? L. Yeah, L is 10 centimeter. So 100 into 10 power 3 into 10 centimeter, I converted into 10 mm. So 10, 100 it became. So 2 into pi by 4. D square is 100 into 200 into 10 power 3. So it became 100, 10 power 3, 10 power 3 cancel. 100, 100 cancel, 100 to cancel, 2 to cancel. Okay, it is cancel, right? I made a mistake here. 100 into 10 power 3 into 100 divided by 2 into 5 by 4 into 100 into 200 into 10 power 3. Here actually this 10 power 3, 10 power 3 cancel. So 100, 100 cancel. 100, this 2, 2, 2 cancel 4. So it is only 1 by pi. It's not 10 pi. If it is there, it is 0.318 mm, right? Delta has to be less than 0.318 mm, but in our question, we have been given with 1 mm. So, as per the question, the gap is too large. Hmm? The gap is too large, and hence there won't be any stresses induced in BC. But yeah, of course, AB we will have same as problem number one, right? There's no change. The same answer will remain as in problem number one. AB 318.3. Fine. Mm. This is the minimum gap. Might be here, I would have asked a question like, what is the minimum gap required so that you need uh, stresses to induce, right? So that would have been a question, right? Suppose if zero point 0.1 mm is the gap, suppose I am rechanging the question. If gap is equal to zero point 0.1 mm given in question, what we'll do? Instead of this 0.1 mm is given means then we'll substitute zero point 0.1 and yeah, it's possible, right? So F is equal to, just if this is equation number one implies F is equal to 100 into 10 power 3 divided by 3 minus 2 into pi by 4 into d square is 100 into 200 into 10 power 3 into divided by 3 into L is 100 into, again this is 1 by 10. Okay, so this we need some attention. This is equal to 100 get cancel, 2 ones are to 2s are this 200. So 100 into 10 power 3 by 3 common, 100 into 10 power 3 by 3 common, 100 into 10 power 3 by 3 times 1 minus pi into nothing is there, 1 by 30, right? So this will be equal to, let's use calculator, pi by 30 minus 1 times 100 into 1000 by 3. So this is equal to 29,842.67 newtons or 29.842 kilonewton, right? This is the stress induced, sorry, force induced in BC if gap is zero point 0.1 mm. Now we can actually compute stresses in AB and BC using the formula here, right? Stresses in AB is what? Stresses in AB is equal to force in AB divided by area of AB. So force in AB is what here? P minus F. So P minus F by 4A. P is, we know, 100 minus 29.842 into 10 power 3 by 4A is 200. So 100, this became 10. So 100 minus 29.842 is 70 times 10 by pi, right? By 10 divided by pi. This is 223.32 megapascal. Fine. So that's it. Now, what is stress in BC? We need to look at free body. So stress in BC is a compressive stress. So minus F by A. Okay, this is tensile stress. AB is tensile and BC is compressive. This is tensile. No, this is compressive. So minus 29.842 into 10 power 3 divided by pi by 4 into 100. So this is 10. So 29.842 into 40 divided by pi, giving me 379.96 megapascal. Compressive, right? Nature is compressive. Sigma BC. Okay, right. So if the gap is smaller than 0.318, so we have stresses. If gap is more than that, it is same as problem number one. Fine. That's it. Moving on. So this all that we have seen is a variety of problems, a step shaft. Now let's see how to solve problems which are not homogeneous, that is made of more than one materials. Okay, this is more no, inhomogeneous problems, non-homogeneous materials. Okay, this is second subdivision of today's topic. Totally, we have three in line in total. One is direct, the step shaft. Second is non-homogeneous material. Third is thermal strains, thermal effects coming in. Fine. So here, let's take a problem directly. Given this is problem number four, right? Problem number four. Given the question given is there is a rigid bar, rigid say plate or something. Here also there is a rigid plate. In between these two rigid plate, there is a pipe, a steel pipe with diameter given. Okay, this pipe diameter is 10 mm steel pipe. This material is steel, and inside we have concrete. And this diameter total is 100 mm. Okay, this also cylinder in shape, and the bottom plate also rigid, and it is fixed. Okay, cannot move. Now, what else is given? The question Young's modulus of concrete is 30 gigapascal and Young's modulus of steel is 200 gigapascal. Now we need to find three things: deflection, undergone, second, stress in concrete, third is stress in steel. Okay, these things we have to find. Let's begin. Just a minute. Yeah, let's begin. Now, I didn't give the load, right? That's important. Without load, it will remain as it is. So this load is given as 100 kilonewton again. P is equal to 100. We need to find what is the deflection the whole thing undergoes. Okay. So and also it's asked to assume to neglect the Poisson effect. Let me move the calculator a little aside so that the screen is visible. Yeah. Right. So let's start. Now, say, let me redraw this. If this is the rigid plate and this is the steel material and this is again a rigid plate. And so if there is a load here, this is going to undergo a deflection, something like this. Say the deflection it undergoes is delta. hmm, If it is delta, now we have again strain displacement relation, um, constitutive relation, compatibility equation, and equilibrium equation. So let's apply one by one. First, I'm going to apply strain displacement relation. So the strain displacement relation, maybe if I want to fix my coordinates, this axis, this is vertical is z, and this is y, and this is x. Right. So what is sigma zz? Because all the other stresses are zero, I'm just directly right. Sigma zz is which is delta by L. Okay, L is the length of the steel plate. This here. Okay, this also has to be given in the question. Yeah, it is given as L is equal to again 20 centimeter. Okay, this is given in the question. Now, sigma zz equal to delta by L is my strain displacement relation. And how about constitutive relation? Again, constitutive relation. Sigma zz equal to E times epsilon zz, right? Now we have compatibility equation conditions. So here for this problem, what does compatibility between the steel and concrete? It says that both the strains has to be same, right? Otherwise, there won't be a compatibility between them, right? So they whatever the amount, because both are rigid at the top and the bottom. So whatever the compression the steel undergoes, the same compression the concrete also undergoes. So this gives us epsilon zz of concrete will be equal to epsilon zz of steel, right? So this implies what is epsilon zz using the constant relation we can write as sigma zz of concrete by E of concrete is equal to sigma zz of steel by E of steel. So this is equal to sigma zz of, maybe I can relate, uh, right? Sigma zz of concrete. And by the way, this is what this is nothing but, okay, there is a error in my notation. This is nothing but epsilon, right? Strain. So this is nothing but delta by L. Both the strains are same, right? So this is nothing but delta by L. So sigma ZZ in concrete will be equal to delta EC by L, and sigma CZ in steel will be equal to delta ES by L. Fine. So these two. Next equilibrium, finally, equilibrium equations. Equilibrium equation tells us the total load P will be equal to the load shared between the concrete and the steel. So F concrete plus F steel will be equal to the total load P. Fine. So load is equal to stress of concrete into area of concrete plus stress of steel into area of steel equal to P. This is equal to sigma of concrete. Let's substitute delta EC by L times AC plus delta ES by L times AS equal to P. Okay, AST here. This implies delta common, L also common, EC AC plus ES AST equal to P. So I am interested in deflection delta. So delta is equal to P divided PL divided by ECAC plus ESAS. Let's substitute everything ESAS. So this is equal to what is P? The problem P is given as 100 certain kilonewton. So 10 into 10 power 3 divided by 30 gigapascal into area is pi by 4 into d square. D square is this 100 is diameter. So 100 square plus 200 into 10 power 3 into AS is steel pipe diameter is given as 10 mm. Pi by 4 into 100, 10 square. So, 10 power 4 divided by this pi by 4 is common. What else? 10 power 3 is common and 10 square is common. So, if I take all these things, pi by 4, so 30, this is 10 power 4, so I took 10 square plus 200. 10 power 3 went out, 10 square went out, pi by 4 also went out. So that's it. So this is equal to, it becomes 10 alone. So 10 pi, no, 4 will go up. 4 divided by 10 pi into 10 square is 100. 100 3s are 300, 3200. Okay, this is deflection in mm, so it's very low. It's of the order of, I guess, micrometer. Let's compute the value. So 4 divided by 3200, 32,000 into pi. Okay. So 3.979 into 10 power minus 5 mm. Okay, it's very low. Fine. But still, this is a final answer delta. Okay. Next question is stress in B. So stress in concrete and stress in steel. Stress in concrete is what? Stress in concrete. This is subdivision B. Sigma concrete will be equal to P concrete, force in concrete by area of concrete. Already we have the sigma concrete here. Okay, I'm just using this particular relation. Say this is equation number 2. Delta times EC by L, right? Delta EC by L. Substitute delta 3.979 into 10 power minus 5 into 30 into 10 power 3 gigapascal divided by length is 20 centimeters. So 200 mm. This is equal to, gives us sigma c directly. 3.979 into 10 power minus 5 into 30 into 1000 divided by 200. Okay. So 0.00597 megapascal. This is very less, but still, this is the answer. Right. And finally, we need to find stress in steel. Stress in steel is what sigma steel will be. We already have this expression, say 3 delta into ES by L. Delta into ES by L. So delta is again there. This will be higher, 3.979 into 10 power minus 5 into 200 into 10 power 3 by 200, because this Young's modulus of steel is higher, so it is taking little more stress. So 3.979 into 10 power minus 2, so which is 0.03979 megapascal. Okay, that's it. Fine, that's it. So this finishes this particular question. Let's take up one more question of this type. Problem number 5. Yeah, problem number 5. So let me write down the problem here. So the distributed loading is, maybe I'll write something important only. Distributed loading is supported by three suspenders bars AB and okay, AB, CD, and EF. I'll draw the diagram so that we know. So there is a three suspender bar here, a fixed support. Sorry, it's fixed at this support. So there is a bar here. There is a bar here. There is a bar here, and this is fixed to uh, maybe a rigid beam. Yeah, a rigid beam here. Okay. Say this is AB, this is BCD, this is EF. And this is made of steel. The middle one is made of steel. The outside one is made of aluminum. And this distance between them is 1.5, 1.5 meters. And there is a distributed loading. There is a distributed loading. The load is acting like a UDL, uniformly distributed load. Okay, this is W. This is not given. This is what we have to find. W is the distributed loading, and all the bars has area value as 450 mm square, and Young's modulus also given. For steel, it is 200 gigapascal. Same for aluminum, it is 70 gigapascal. And allowable stress is also given. Allowable stress for steel is 180 megapascal, and allowable stress for aluminum is 94 megapascal. Okay, allowable stress means that's a maximum it can allow. Apart from that, it cannot withstand. Right? That's the meaning of allowable stress. It cannot exceed that particular value, both aluminum as well as steel. What happens if it goes more than that? It will starts to fail. Right? That's a limit in design that we allow. Right. So what is the thing we have to find is what is this W? Okay, what is the maximum intensity of the distributed load? Maximum intensity of the distributed load. That's it. Okay, this is what we have to find. Now, shall we start? So, this is actually a design problem. We need to find the maximum load. By the way, usually in real scenarios, we know the load. We need to design this areas, area of steel and area of aluminum. But yeah, in here the area is given. We need to find what is the maximum load it can allow. Okay, both are moreover same kind of problems with one unknown, right? Either this or that. Now let's begin how to solve. Uh, Fine. Maybe I'll do one by one. Maybe we can write the equilibrium equations. Equilibrium equation. What this equilibrium equation tells, the total load will be equal to, yeah, W into, okay, distributed load. This is distributed per meter, W per meter. So there are 3 meters. So I am going to use 3W is my total load. This is equal to load in aluminum plus load in steel plus load in aluminum. So 2PAL plus PST is equal to 3W. Okay, this is my equilibrium equation tells us. What else we can do? We can use, yeah, we can use compatibility. What does compatibility tells? Compatibility tells us that the elongation, since it's a rigid B, it's attached to, so the elongation in steel should be equal to delta ST is equal to delta aluminum, right? Because it's a rigid thing, it cannot undergo more than ununiform thing, and W is acting uniformly, so both is undergoing uniform elongation, the both the steel and and the aluminum. Where the difference will come, yeah, difference will come in stresses. Each of them will take different loads, right? So this is done. Then what else we can do? Delta, yeah, we can use the constitutive relation and the strain displacement relation to find expression for delta st. What is delta st? Delta st is equal to pst into pl by ea. A is common, so a into est, right? And similarly, delta aluminum will be P aluminum L by A E aluminum. So when we substitute this, we'll get PST L by AE EST is equal to P aluminum L by AE aluminum. So since LL is same, cancel, AA cancel. So we can able to find a relation between PST and P aluminum. Done. It's solved because we already have this equation. Here the everything we have, right? Extra one unknown is there. So two unknown, one equation is there. So we can able to solve it. Let's find this relation. So PST will be 200 divided by 70 times P aluminum. So 20 by 7 is 2.857. Right. So this is done. So what is the stress in aluminum and steel? Sigma, okay, finding stresses. Sigma ST will be equal to PST divided by area. Okay. Uh, 2.857 P aluminum by area. Okay. Can we substitute this and write in terms of W so that it will be easy for us to substitute everything back? This we will use in a while. Before that, I'm going to substitute this thing in this is equation number 2. Assume it is 2. Equation 2 in 1 implies 2p aluminum plus 2.857p aluminum is equal to W, 3W. So this is 4.857 P aluminum equal to 3W. Therefore, P aluminum is equal to 3 divided by 4.857. 3 divided by 4.857, 0.618 W. Okay. This is P aluminum and P steel is, so out of this W, it's taking 61 percentage, and yeah, that is steel will be not like yeah, steel will be 2.857 times 0.618. This is 1.765, but yeah, there is one more W, no? So this is 3W, right? So correct. I thought 1W. Fine. So this is P aluminum and P steel in terms of W. Now we are ready to substitute and get the answer for W. Allowable, right? So this is equal to P steel is 1.765 W by A. This should be less than how much steel can only withstand? 180 megapascal. Okay, so this is less than 180, and one this area also is there. Area is 450 mm square. So this is equal to W is less than 1.180 into 450 divided by 1.765. Okay, this reciprocal times 180 times 450. So this gives us W less than this Newton per meter. So it's giving me 45876.08 newtons per meter. So W is less than 45.876 kilonewton per meter. Okay, this is for steel. And for aluminum, sigma st, this is for steel. For aluminum, sigma aluminum equal to P aluminum by area. So sigma aluminum is equal to P aluminum is 0.618. Area is 450. This should be less than, allowable is 70. Should be less than 70 into 10 power 3. Did we substitute a 10? Okay, wait. Allowable is, sorry, 94, right? Yeah, that's thanks for us. 94 this is. So this gives us W should be less than 94 times 450 divided by 0.618. So this gives us 68.45 kilonewton per meter. Okay. So out of this, which is the minimum, that is the final answer, because once W cross this, it's going to fail steel, right? So that's it. Fine. So this is the final answer. So the minimum value it can withstand, sorry, the maximum value it can withstand is 45.8. Okay, that's it. Fine. So with this, we'll move on to the last variety of problems, that is involving thermal strains, temperature strains. Problem category number 3, thermal strains. Let's quickly recap few concepts before we proceed with the problems. So in general, we can write the strains as the observed strain as a lot of strains. One is the mechanical strain that we see the force by area. Another is strain due to temperature, this thermal. Okay, and a lot of other strains due to electrical, due to hy- hydroscopic, a lot of other strains can come. But we are majorly focusing on the mechanical strain and the thermal strain, right? And it's important to note that only mechanical strain enters the constitutive relation. And this thermal strain is given by what? This thermal strain is alpha times delta theta. Delta theta is the change in the temperature, right? No, it's a tensor, so identity. Fine. Okay. And observed strain is sum of mechanical strain and thermal strain. Okay, this is what we need to. This alpha we call as coefficient of coefficient of thermal expansion. This is important because, in fact, the reason for choosing steel and concrete in a reinforced concrete structure, one of the reason is this alpha. If the alpha value of two materials is closer, in the case of rise in temperature, both are going to expand uniformly and or contract uniformly. If we have a huge variation in alpha, then what will happen? One will expand more, another will expand less. So that will cause a problem, right? So that's so. And also, in case of railway tracks, we have expansion joints. So there will be a thermal expansion of railway tracks, and hence there will be a expansion joint in between the tracks. So it has a lot of applications in other things. So it's important, right? So I think let's go with the problem that we have here. Let me write the problem. So problem number 6 for the day. Problem number 6. So given same a shaft, stepped shaft subjected to a change in temperature delta theta is equal to 40 degrees Celsius. Okay, and this is same 4a, this is alpha, and same this is a, this is alpha, this is 2l, this is l. Okay, same ABC, it's the our same shaft. I'm not changing any of the dimensions. So alpha value is given as 20 times 10 per minus 6 per degree Celsius. The value is given as 200 gigapascal. Okay. Now, what we need to find? We need to find the displacement of B, that is delta B is equal to what, and displacement of C, delta C equal to what, and stresses in AB, sigma AB equal to what, and stresses in BC, sigma BC equal to what? Okay, these four questions. This is what actually we are finding throughout for various cases. Okay, so let's begin to solve this particular problem. Yeah. So again, what is the first step? First step in a solution will be always free body diagram. The first step is drawing the free body diagram. So if I draw the free body diagram for this, which going to look like, so AB is here and BC is here, A, B, B, C, and yeah, it's 4A, it's A, and it's 2L, it's L. Okay, otherwise alpha and E are same. Now, is there any force, by the way? Is there any force? Uh, Actually, in the question, there is no force given, but they have given a change in temperature of 40 degrees Celsius. So it's going to expand. But is there any force? No, there is no force here. So, but there is strains, right? There is expansion because of thermal. So let's see what is the this observed strain. What is the observed strain of AB? Due to rise in temperature, maybe this AB will undergo something like this. It's going to expand, say, delta. So we have a change, right? So this is equal to delta B divided by, this is 2L. Okay, this is delta B divided by 2L. Now, what is observed strain? This is nothing but mechanical strain plus thermal strain. Thermal strain is alpha into delta theta of AB, right? So this is what in AB is. And what is the mechanical strain in AB? It's zero because there is no load applied. So mechanical stress is equal to zero. So epsilon AB, which is I'll write directly this as delta B by 2L is equal to 0 plus alpha delta theta of AB. So delta B, displacement in B is equal to alpha delta theta times 2L. Let's substitute everything. Alpha is 20 into 10 power minus 6. Delta theta is 40 into 2 into L is 10 centimeter, right? 100. yeah, 100. So this will be equal to 1, 2, 3, 4, 10 power 4, 2 4s are 8, 8 2s are 16, 16 into 10 power minus 2. Okay, 0 0.16 mm. This is delta B. Fine, right. Next question is delta C. So delta C, for delta C, we will take the free body of BC portion. So from free body of BC, okay, what is observed strain in BC? Delta observed strain will be delta BC by L, right? Delta BC is nothing but delta C minus delta B by L. So this is equal to mechanical strain, again mechanical strain of BC plus thermal strain alpha into delta theta. Fine. So delta C we don't know, minus delta B divided by length of BC is what again? This is 10, right? Okay, the 2L is it's 100. This is equal to, is there any mechanical strain in BC? No. Why? Because there is no load. So it's 0 plus alpha is 20 into 10 power minus 6 into 40. So delta C is what I need, equal to delta B is 0.16 plus 20 into 10 power minus 6 into 40 into 100. So 0.16 plus 10 power 2, 10 power 3, 10 power 4, it will become 10 power minus 2. So 8 into 10 power minus 2, 0.16 plus 0.08 will give us 0.24. Okay, mm. This is delta C. Right. Next question. Next question. Stresses in AB and stresses in BC. Is there any stress in AB? Stress in AB is given by, this is subdivision number C, right? Stress in AB is given by sigma AB equal to force in AB by area of AB, right? Is there any stress in AB? No, because there's no force. And again, BC also same, there is no force, external force. Of course, there is strain, but doesn't mean that there is stress, right? It's just freely expanding. If and only if the expansion is restricted, it will be subjected to a stress value. So it is 0. This is 0. Okay, similarly, sigma BC will be equal to 0 megapascal. This is D. Then this finishes the problem. Okay. Finally, let's finish it off with the final problem for the day. Problem number 7. So everything is coming here, like the gap as well as the temperature. So there is same stepped shaft. So there's a gap here, delta. Same, this is 4a and this is 2l and this is a, this is l. A is this pi by 4 into 10 square. L is 100 mm square, and E is 200 gigapascal. Alpha is 20 into 10 power minus 6, and delta theta is same 40 degrees Celsius. Fine. Now just a minute. Charge 17, yeah, it will come. So we need to find two things. One is the minimum gap required for no internal stress, zero internal stress. And option B, suppose if gap equal to 0.5 mm, find the stresses induce in AB as well as BC. Okay, this is the question. This is A, B, C. Okay, let's begin the solution. Yes. So whenever there is a gap, the procedure that we adopt is we assume that there is no gap and draw the free body diagram, proceed solving, and then we equate the displacement at that particular location with the gap value. So assume there is no gap. Assume there is no gap or the gap is closed, and draw the free body diagram. Let's draw the free body diagram. This is first shaft. This is second shaft. So if there is no gap, what will be coming? It will be subjected to some internal stress, internal force, right? Induced force. So this is equal to F. And this F will again, as per Newton's law, it will come here and it will come here. So both the bars are in compression, right? This is A, B, and B, C. Fine. This is the free body diagram. That's simple. So now we need to find the minimum gap. So uh, we'll find the displacement at C and we'll equate with the gap so that we can able to get the condition is this F has to be positive, right? Because we assume the compressive stress, so it cannot be in tensile. So that's a idea to solve this problem. So I'm going to find the deflection at C. For that, I need deflection at B. For that, I need the strain, right? So let's take AB. So upsurge strain in AB will be equal to mechanical strain in AB plus thermal strain in AB, alpha delta theta. Right. So upsurge strain in AB is what? Yeah, there is a force induced. So maybe if delta A is zero, A is fixed support. So delta B by 2L is equal to what is the mechanical strain in AB? Mechanical strain in AB is nothing but F by A. Correct. F by A. Right. Minus F by A. Okay. This is 4A, na? Yeah, this is 4A. Why minus F by A? 4A? Because it's compression. So I'm putting a minus sign here. Fine. This plus alpha delta theta. Now from this, can we find delta B? Of course, we can. Yeah, but there is a unknown F. Let it be. Apart from that, alpha is known. Delta theta is known, A is known, L is known. So there are two unknowns, delta B and F, okay, in this equation. And similarly, we can write epsilon BC observed as epsilon BC of mechanical plus alpha delta theta. So this implies epsilon BC of my observed is what? Epsilon BC is delta BC by L, right? L. Yeah. Delta BC is delta C minus delta B. So delta C minus delta B divided by L is equal to what is mechanical strain in BC? Yeah, there is a force F. So let me write in this color minus F by area. Okay, this is mechanical strain plus alpha into delta theta. Okay, so this implies maybe this is 1, this is 2. Equation 1 implies delta B we can find, right? Delta B equal to minus 2FL by 4A plus alpha delta theta FL, 2 alpha delta theta FL, right? So this implies F is the unknown. Wait a minute. F is not there in the second expression. How does it came? Cannot come. Yeah, F is the only thing unknown. Maybe we'll substitute it back. Let's say this is 3. Now equation 1 implies we done. Equation 3 implies, or equation 2 implies, equation 3 in 2 implies delta C minus delta B by L equal to minus F L by A. I'm bringing this L up plus alpha delta theta into L. Okay. So this is equal to delta C equal to delta B minus FL by A plus alpha delta theta into L. So substitute everything back, we'll get delta C. So delta C equal to minus 2FL by 4A. Okay, this I can write as FL by 2A plus 2 alpha delta theta L minus FL by A plus alpha delta theta L. Okay, so this is equal to 3 alpha delta theta L minus this is 2 2, so 2A 3FL. Okay, so 3 common, L also can be common, alpha delta theta minus F by 2A. Fine. That this is equal to actually gap, this delta. Okay, right? So if delta C is nothing but delta C, because we initially assumed there is no gap, but the question there is a gap. Now, what is the minimum stress, minimum gap required so that no internal stress should be there? For that, I need an expression in terms of F, right? So let's substitute alpha delta theta minus F by 2A equal to delta by 3L. So alpha delta theta minus delta by 3L equal to F by 2A. So therefore F is equal to alpha delta theta times 2A minus 2A delta by 3L. Okay. Did I miss this E anywhere? Anywhere did I miss E? Okay. Oh, yeah. I didn't use E at all, right? So this is a huge problem. Actually, this is stress, whatever I have written, force by area. Sorry for that. So this has to be E, right? So E should be there. E should be there. And here also E should be there. So very sorry for about this. So 1 and 2. Here also E will be there. Here also E will be there. Here also E will be there. The careless mistakes that I should avoid. E, E, E. Right. I think I have yeah, rectified it, right? To AE, AE. So to A, E will come. Okay. I hope it is rectified now. Okay. To A, yeah, fine. So this is F. Now for F to be positive, what should happen? Is there anything common so that we'll see it very clearly? If anything common, yeah, 2A is common, E is common. Uh, Rest of the thing, alpha, delta, theta minus this delta by 3L. Now for F to be positive, for F to be positive, this alpha delta theta must be greater than delta by 3L, which means delta should be less than 3L alpha delta theta, correct? Okay. So delta should be less than 3L alpha delta theta for F to be positive. So this implies delta is less than 3 into minimum gap, right? 10 centimeter into 20 into 10 power minus 6 into 40. So delta less than 3. This is 10 power 2. This 10 power 3, 10 power 4. So we'll have 10 power minus 2 and 3 2s are 6, 6 4s are 24. So 0.24 mm, delta less than 0.24 mm. This is the minimum gap. Okay, right. If my gap is more than 0.24 mm, what will happen? Um, there won't be any internal stresses induced, right? It's same as problem number 6, right? Now, yeah. In the next question, they have given gap to be 0.5 mm. Yeah, it should have been zero point 0.2. Rectify. Maybe let's take zero point 0.2 because 0.5 mm again, it should be no internal stress will be there. So there's no point in doing the same. I'm going to do assume a gap to be if gap equal to zero point 0.2 mm. What are the stresses in use? So directly we will find this force. Once we find force, we can find the stresses, right? So force will be alpha delta theta 2a minus 2a this gap value times c. So 20 into 10 power minus 6 into 40 into 2a common. Gap is zero point 0.2 divided by 3 into 100. 2 into A is, I forgot what is A, 5 by 4 into 10 square. 5 by 4 into 100. 2A into E is 200 into 10 power 3. Okay, so this will be 2 4s are 8, 10 power minus 4. minus this 2 divided by 10. So 2 by 3 is 0.667 into 10 power minus 3. This will be 5 by 4 is there. Okay. 1 are 2 sir. 2 ones are 200 sir. So 10 square, 10 square, 10 power 4, 10 power 7. Pi into 10 power 7. So F will be 8 minus 6.67 will be 1.33. 1.33 pi times 10 power minus 4 times 10 power 7, which is 10 power 3 Newton. So kilonewton into pi. 4.178 kilonewtons. Okay, this is F. Okay, now stresses induced will be sigma in AB will be F by area of AB. F by area of AB. And sigma of, okay, let's finish it off. 4.178 into 10 power 3 divided by area of AB is 4 times pi by 4 into 100. Okay. So 4.187 into 10 power, this 100 will become 10. So into 10 by pi. So I'm getting 13.3 megapascal, right? Sigma AB. And sigma BC will be force by area. So because in the free body, only F is there by area of BC. Force is 4.178 into 10 power 3 by area of BC is only pi by 4 into 100. This is 4 times 4.178 by pi. 5.32 megapascal. Okay, that's it. Fine. Okay, so with this, we come to the end of the today's problem solving session. Let me just quickly recap the whole exercise. So today we saw three varieties of problem. First, all are related to axial members, boundary value problems involving axial members. So first we saw in general how to draw. The steps are simple. First we draw the free body diagram, then we apply the equations one by one. The equilibrium equation, compatibility equation, strain displacement relation, constitutive relation, everything we apply and we solve for the unknowns, right? That's the order. And we what else we saw? We saw how if there is a gap, the usual procedure that we follow is we assume there is no gap and we equate the displacement at the end with the gap. Okay, and then we see that for minimum gap to be there so that the stresses are coming, otherwise the stress won't come if there are no minimum gap. Then we saw for non-homogeneous material, moreover the same, we have to apply each of them one by one and then we have to solve, right? Compatibility condition is very important. That's what actually will solve the problem. Okay, only strain displacement, constitutive relation, equilibrium relation will pose another unknown, so which we need one more equations to solve. Fine. So finally, we saw thermal strain. We saw upsurge strain equal to mechanical plus thermal strain, and we saw how to solve the problem of the strain. Okay. So with this, I complete problem solving session of week number 6. Thank you all.